Good morning, everybody. Welcome to another exciting morning at Chemistry 1211 with your host, me, Dr. White. Due to technical difficulties, the original video doesn't exist. So I am redoing this one. As you know, on Monday when we did it live, the first half of this lecture dealt with the answers. I went through the answers for test number one. And I always remove that from the videos that I post on YouTube. So it's just been removed. All right, today we're going to talk about molecules that involve covalent bonds. So let's get started. One thing, since this is a remake and there are no students here, when I give you an example, I'll say hit pause, and then you'll be able to do your problem, take your time, and then play it again, and I'll go through the answer. So let's get going. Now, when we talk about covalent molecules, one of the important things is doing Lewis structures. And remember, molecules or chemical bonds, covalent chemical bonds, involve electrons that are being shared. Where ionic, you have transfer of one electron from one atom or group of atoms to another atom or group of atoms. For covalent bonds, you have shared electrons. All right, so if you were reading the book, you would see that the covalent bond model is between similar or identical atoms. The important thing, it involves electron sharing. And if you're reading the book, they make a thing about the structural unit is a molecule. Well, sodium chloride, I call a molecule too, but I understand why they do this. You don't have to worry about this. All right. Now, what is a covalent bond? A covalent bond, in your book, it says a chemical bond resulting from two nuclei attracting the same shared electrons, or as I like better, what is a covalent bond? It's a chemical bond between two atoms resulting from the sharing of pairs of electrons. Another way of saying that, it's the sharing of pairs of electrons between two atoms. And it's time for Dr. White to be subtle. Get the message? So you should know that a chemical bond results from the sharing of pairs of electrons between two atoms. All right, let's look at one of the simplest molecules around, and that's hydrogen. And I'm talking about hydrogen gas, not the element hydrogen. Now, each hydrogen atom has one electron, which means it only has one valence electron, and it exists as hydrogen gas. Now, how do you show that? Well, if I were to ask you to draw the Lewis structure for hydrogen gas, each hydrogen has an electron in its outer shell. And this hydrogen says to that one, you've got an unpaired electron, I've got an unpaired electron, let's share. And they do. And that's a covalent bond. And a lot of times I'll just say, instead of a covalent chemical bond, I'll just say covalent bond, which is a chemical bond. And therefore, that's the structure of that. And only valence electrons are ever involved in covalent bonds. And you remember, let me open it up because I don't have it open. If you look at the periodic table, what you should now see, let me check because I can't use thumbs up people today because they're not out there. All right. You should be seeing the periodic table. And how do you find the outermost valence electrons? You look at the number on top of each column. Hydrogen is in this column, even though it's not an alkali metal, it still is in this column because it has one valence electron, like lithium, sodium, potassium. Magnesium has 2, calcium 2, my favorite carbon has 4, nitrogen 5, oxygen 6, bromine 7, and argon, which I worked with in our grad school, has 8 valence electrons. And these are the electrons you use for a Lewis structure of now a compound. Now, I need to make something clear that some of your colleagues ask questions about, or one particular, and that is when you're doing a Lewis structure for an element, you have one dot on each side before you double up. And for a Lewis structure of an element, you never, ever have more than 2 dots on the side, never more than 2. However, Lewis structure for a molecule, those rules are not true, or I shouldn't say true, are not followed, and you can have more than 2 dots or valence electrons between elements in a Lewis structure. And you'll see that coming up soon. Now, when we talk about covalent bonds in molecules, we're looking at the valence electrons. And there are 2 types of valence electrons. One are the bonded electrons. By the way, switches on for the slide. And those are a pair of valence electrons that are shared between atoms in a covalent bond. We call those the bonded electrons. Now, sometimes certain elements have pairs of electrons around them that are not involved in a chemical bond, and we call those non-bonding electrons. Those are pairs of valence electrons that are not involved in electron sharing. So you have bonded electrons, pairs of electrons between atoms that are being shared, and then you have non-bonding electrons, which are pairs of electrons that are not being shared or not involved in electron sharing. Guess what time it is? It's practice Lewis structure for key molecules. Well, let's look at one. Now, if we look at chlorine, how do you draw the Lewis structure for that? Well, first of all, you have to know chlorine has 7 valence electrons. And if I draw a chlorine, there is its structure, or Lewis structure. Now, let me make the dots a little bigger. This way you don't have to get your microscope out to see them, or magnifying glass. And if I had another chlorine, guess what? It has 7 valence electrons. And this chlorine says to that one, oh, you've got an unpaired share electron. I've got an unpaired. Let's share. And they do. And the rest of the electrons that are non-bonding are still there. Now, if you look at the pair of electrons in the red box, these are the bonded electrons. If you look at all the other pairs of electrons around the 2 chlorines, and these are not involved in a chemical bond, and we call those the non-bonding electrons. So molecules can have bonded, involved in sharing, and non-bonding electrons. and they're always pairs. When you're dealing with covalent bonds, you're dealing with pairs. Remember, pair means two. All right, let's try hydrochloric acid. Oops, let me get the right color. Hydrochloric acid, I'll teach you more about later in the semester, has a hydrogen, which is one valence electron, and a chlorine, guess what, still has 7 valence electrons. Now, on a test, you don't have to write this, but this helps you see it better. Here we have one unpaired electron hydrogen, one unpaired on chlorine, and the hydrogen says to the chlorine, hey, let's share electrons. And they do. And this would be the correct answer for the Lewis structure of hydrochloric acid, HCl. Now it's time for Dr. White to share because I don't want to keep all the fun to myself. So I'm going to let you try water, but I'm going to help you out. Let's get to my whiteboard. And now and if you were to see it sometime on something I would send you called a test, it would say draw the Lewis structure for, and you'd say 3 points each, you'd see water. Well, I'm going to help you out. Hydrogen has 1 valence electron, and oxygen has 6 valence electrons. Remember, look at the periodic table. And now I'm going to give you some time to do that. Hit the pause button if you need more time. Time's up. Let's take a look at this. How do you do it? By the way, I hope you hit the pause button so you had all the time you needed. All right, now hydrogen has 1 valence electron. Oxygen has 6. Now this hydrogen says to this oxygen, let's share. And they do. But there are 2 hydrogens in water, H2O, and there's another hydrogen with 1 valence, and here's an unpaired on oxygen and 1 for hydrogen. This hydrogen says to the oxygen, let's share valence electrons, and they do. And this is the structure, the Lewis structure for water. Now, if we look at this, we can see between the oxygen, this hydrogen, a pair of electrons, and the oxygen, this hydrogen, a pair of electrons, and these are the bonded electrons. So if you happen to be at a party, like a Zoom party, or sometime in the future when you see someone drinking water, you can say, do you know you're drinking a molecule that has 2 chemical bonds in it? And it does. This one and this one. Wait, by the way, people don't like hearing chemistry when they're drinking water. All right, let's do another one because these are fun. And this is ammonia, NH3. And I'll help you out, but you should be able to find this for yourself. Nitrogen has 7 valence electrons. Hydrogen has 1 valence electron. And why don't you draw the structure for ammonia? And if you need more time, hit the pause button right now. Just check to make sure we're still recording. All right, time's up. All right, now, hydrogen has one valence electron. Oh, I made a mistake here. This should be 5. I was thinking of chlorine. And see, even Dr. White makes mistakes. And nitrogen has 5. Now, notice there are 3 hydrogens. And this hydrogen says, I've got a single valence electron. You do, let's share. And the others do the same thing. So how do you draw the Lewis structure for ammonia? The non-bonding electrons here are still there. Don't forget those. I'll mark it wrong. And then this hydrogen shares an electron with the nitrogen. So does the next one. And so does the third one. And if you notice, there are 3 covalent bonds in ammonia, NH3. Now, one of the things I talked about earlier, and I should bring up now, is if we look at hydrogen, this one, notice how many electrons, both bonded and non-bonded, does it have? And the answer is 2. Now, there's the octet rule. Remember, octet means 8. And the octet rule is atoms want to lose, gain, or share electrons so they have 8 valence electrons around them. The one exception is hydrogen. Hydrogen's octet rule number is 2. And notice this hydrogen has 2 electrons, so it's happy. However, let's look at the nitrogen. And if we look at all the electrons that nitrogen is either sharing or has alone as non-bonding electrons, we've got 2, 4, 6, 8, and it has its octet, and it's happy too. And that's why NH3 ammonia exists as NH3, because everybody has their octet. But remember, the octet for hydrogen is 2. All right. Now, if we only had one pair of electrons being shared between atoms, life would be pretty boring. Chemistry would be pretty boring. But good news, Mother Nature, the greatest of all chemists, didn't stop with this one pair of electrons being shared. There are more, and we have names for that. And it's time for Dr. White to be subtle, very subtle. Hint, know this. And what should you know? There are 3 types of covalent bonds. The first one is a single bond. And what is a single bond? 2 atoms which share one pair of electrons. Single bond, sharing a 1 pair of electrons. And for those of you who know baseball, if you go to first base, what have you hit? A single. First base, 1 pair of electrons. Now, you can have 2 pairs of electrons being shared between 2 atoms, and we call that a double bond. And a double bond consists of 2 atoms sharing 2 pairs of electrons. And going with the baseball analogy, if you hit a double, you go to second base too. So you have a single bond one pair of electrons being shared, and you have a double bond, two pairs of electrons being shared. And there's more. You can also have a triple bond. And a triple bond is in situation, a chemical bond in which two atoms share three pairs of electrons. So triple bond, you have three pairs of electrons being shared between two atoms. So let's go through everybody. Class participation. What's the first type of covalent bond? Single bond. What's the second type? Double bond. And what's the third type? Triple bond. And if you look at my whiteboard, let's check because there are no thumbs up, people. I got to check myself. I can't ask for thumbs up, people, because you're not out there, because this is a remake. But anyways, this is important. And if we were at COD, you'd be waiting patiently while I write this on a whiteboard. All right, first covalent bond, single bond. And how many pairs of electrons are being shared? One. Second type of covalent bond, double bond. How many pairs of electrons are being shared? Two. And finally, triple bond. And how many pairs of electrons are being shared? Three. And it's time for Dr. White to be subtle again. And I think I mentioned when I took notes, if I put stars, those are the ugliest stars in the world. Let me redo those. I can do better. And I will. That's better. If I put three stars, it means it's important. And if I also added this with an arrow, I knew I better learn that. Hint, you should too. And once again, let's go through it. What are the three types of covalent bonds? Single bond, double bond, triple bond. You should remember single bond, one pair of electrons being shared. Double bond, two pairs of electrons being shared. Triple bonds, three pairs of electrons being shared. And now let's go and look where we can find single, double, and triple bonds. Let's look at nitrogen. And nitrogen, I'll get it right this time, has 5 valence electrons. And if we go like this, here's one nitrogen. Let's do a second one, the Lewis structure. And this nitrogen says to that one, hey, I've got 3 unpaired electrons. You've got 3 unpaired electrons. Let's share. And they do. The non-bonding electrons are still there. And here's the Lewis structure for nitrogen. nitrogen gas. Right now, you're inhaling that in the air you breathe. And what kind of bond are between the two nitrogens in nitrogen gas? And what type is that? Let's see. One, two, three pair of electrons, and that's a triple bond. And the next time you see a friend, neighbor, or loved one breathing, inhaling, you can tell them, you know, you're inhaling nitrogen gas, which has a covalent triple bond. People don't like to hear chemistry when they're inhaling. And that's true. And now it's time for me to share and let you try one. And why don't you draw the Lewis structure for oxygen? And oxygen gas is O2. Now, oxygen has 6 valence electrons. And since there's no one here, you can hit the pause button to give yourself all the time you need. Go. Time's up. Let's do it. And if we take one oxygen atom and draw the Lewis structure, it looks like this. And the second one looks the same. And this oxygen says to that one, I've got 2 unpaired electrons. You have 2. Let's share pairs of electrons. And the non-bonding electrons are still there. This oxygen has 2. The next oxygen has 2. The non-bonding electrons are there. And the question is, what kind of chemical bond, covalent chemical bond, is between the 2 atoms of oxygen? And they're 2 pairs, and we know that's a double bond. So next time you see someone breathing, you can tell them, when you are inhaling air that contains oxygen that's keeping you alive, and that has a covalent double bond, 2 pair of electrons being shared between 2 oxygen atoms. And you can amaze people with your knowledge of chemistry. Let's do another one. And this is hydrogen cyanide. And I'm going to let you do that one your own first, and then I'll do it. All right, draw the Lewis structure for hydrogen cyanide. Hydrogen, you know how to look up, has 1 valence electron. Carbon has 4 valence electrons, and nitrogen has 5 valence electrons. I'll give you a hint. Carbon has to be in the center. So go, your turn. By the way, if you need more time, hit the pause button for those who are watching this video. All right, time's up. How do we do this? Well, hydrogen has 1 valence electron. Carbon, which is going to be in the center, I gave you a hint, has 4. And nitrogen has 5. Now, this hydrogen says to the carbon, I have 1 unpaired electron, you have, let's share. And this is spoken for. Now, this carbon says to the nitrogen, well, I'm sharing 1 with hydrogen, but I have 3 unpaired electrons. You have 3 unpaired valence electrons. Let's share. And they do. And the non-bonding electrons over nitrogen are still there. So in hydrogen cyanide, what kind of covalent bonds are in the molecule? Between the hydrogen and carbon, we have a single bond. one pair of electron being shared. Between the nitrogen and carbon, there are three pairs, count them, they're there, of electrons being shared, and that's a triple bond. And that's how you do hydrogen cyanide. Now let's do one more, and I'm going to do this one for you, and that's carbon dioxide. And CO2 is the gas. If you ever look at pop, remember Dr. White's from Chicagoland, and the stuff in the carbonated liquid that comes in bottles or cans that's non-alcoholic, we call pop, that has CO2. That's the bubbles you see in there. If you buy beer or sparkling wine or champagne, if you're old enough, that also has bubbles, and that's CO2. And when you burp, most of your burp is carbon dioxide, CO2. So how do we do that? Carbon is going to be in the middle to make this work. And if you don't believe me, try another way and you'll see it doesn't work. And it has 4 valence electrons. You know how to look that up. Each oxygen has 6 valence electrons. Let's clean this up. See, Dr. White can make mistakes even when he's alone. All right, now how do we do that? There are 2 oxygens. So I have my 2 oxygens, my carbon. Let me just check, make sure you're seeing this. And you are. And this oxygen says to the carbon, I have 2 unshared electrons, single electrons. You have 2. Let's form a double bond. And they do, and that takes care of these electrons. And carbon says to the other oxygen, well, now I only have 2 valence electrons available. Oops, forgot the dot there. You have 2, let's share. And they do. And this would be the Lewis structure for carbon dioxide. Now, I could ask on a test, what type of covalent chemical bonds are in CO2? After I asked you to do this, and you would say, ooh, 1, 2, they're both the same, 2 pairs of electrons being shared between the oxygen and the carbon, and that's a double bond. So in carbon dioxide, CO2, there are 2 double bonds. And the next time you see someone drinking pop, you can tell them that if you want to. Or if you don't want to, don't. Now, as I mentioned, valence electrons, number of covalent bonds, you need at least 1 vacancy to form it. And you don't have 2 vacancies, or you have 2 unshared electrons for a double bond, 3 for a triple bond. And this sort of helps you know why certain molecules have certain types of atoms. Now, I'm going to skip exceptions. And before we go this, I just remembered I forgot to mention something. Let's go to HCN again and remember the octet rule. And this is a good way to check that you do it right. How many shared electrons or its own does hydrogen have? And the answer is 2. And remember, hydrogen's octet is the exception 2. But now let's look at carbon. And how many electrons shared and unshared does it have? And if we look in the blue box and you count dots, valence electrons, there are 8. So it has an octet. And now let's look at nitrogen and how many shared and unshared electrons? 2, 4, 6, 8. It has 8. So everybody's happy because hydrogen has its octet of 2, carbon has its octet of 8, which is an octet, and nitrogen too. So that's always a way you can check, did you do it correctly? Now, let's look at when we're dealing with Lewis structures involving polyatomic ions. And these are molecules that have ionic bonds and covalent bonds. And before we do that, I have to point out something very important. And that is, look at the periodic table. This is important. Alkali metal, not hydrogen, alkali metal and alkaline earth metals always form covalent bonds. I'll say that again. Alkali metals and alkaline earth metals, meaning alkali metals, lithium, sodium, potassium, the other ones, but we won't talk about in this class, and alkaline earth metals, magnesium and calcium, strontium you use in your lab, barium, but in real life, we'll just talk about magnesium and calcium. These always form ionic bonds. They always give up electrons. And you learned previous lecture that lithium, sodium, and potassium always form a +1 cation, positive charge, and magnesium and calcium always form a +2 cation. Remember, +1, +2. Alkali metals, alkaline earth metals never, ever, ever form covalent bonds. So let's look at what that means. And if we look at here, KOH, draw the Lewis structure for potassium hydroxide. Well, let's go to my whiteboard. And if I look here, I need to change the color of the ink I'm using. And let me first erase it. All right, KOH, potassium hydroxide, also known as potash, because it was originally found in the wood underneath the pots we cooked in when people used to cook over a fire. And how do we do this? Well, potassium has 1 valence electron, oxygen, 6 valence electrons. And you know how to look at the periodic table. Hydrogen, 1 valence electron. Now, potassium is a alkali metal and it never forms a ionic bond. Never. I've never found the exception to what I just told you. So it's going to form its +1 ion. You learned how to determine what ion, but oxygen has 6 valence electrons and hydrogen has 1, and it says let's share. And if we look here, hydrogen has its octet 2, But if we look over here, oxygen only has 7. It wants 8. How does it do that? Well, where does this electron go, which left potassium? It goes to the oxygen, and this forms the hydroxide anion. So between these two, that's an ionic bond. Transfer of 1 or more electrons. The potassium transferred its electron to oxygen or the hydroxide. And in between the hydrogen and oxygen is a covalent single bond. So in this molecule, potassium hydroxide, there's both an ionic bond and a covalent bond. All right, I'm going to share the fun. It's your turn. Another important molecule used in the United States heavily is sodium hydroxide. And sodium has 1 valence electron, oxygen 6 valence electrons, and hydrogen, it has 1 valence electron. And now I'm going to let you try draw the Lewis structure for sodium hydroxide. And while you're doing that, I need to refill my water bottle. I'll be right back. Good news, I'm back. All right, let's do the Lewis structure for sodium hydroxide. Now, sodium, being an alkali metal, never forms a covalent bond. It forms a cation, a +1. Oxygen has 6 valence electrons. Hydrogen has 1. They share. Where does the electron that sodium had? It goes to the oxygen and forms the hydroxide polyatomic anion. And if you notice, oxygen has 8 valence electrons, an octet. Hydrogen, 2 valence electrons, it's octet. And between the sodium and the hydroxide, there's an ionic bond. And that's how you do. Oh, let's do one more. And this one I think Dr. White will do for you. And let's look at potassium cyanide, KCN. And if I were to ask you to draw the Lewis structure, potassium has 1 valence electron, chlorine 4 valence electrons, and nitrogen 5 valence electrons. And if we look at this, how do we do it? Well, potassium, as you learned, is an alkali metal, always forms a cation for an ionic bond. Now, carbon has 4 valence electrons, nitrogen 5, and carbon says, oh, I've got 3 electrons single, you've got 3, let's form a triple bond. And they do. And if you look here, nitrogen now has 8 valence electrons, it's octet. But carbon, oh, it only has 7. But wait, what happens to the valence electron that potassium lost to form the potassium cation. It goes to the carbon. Now, this has an extra electron, so it has a negative charge, and this is the Lewis structure. And now carbon has its 8 valence electrons. And if we look at this, the bond between the potassium and the cyanide anion is an ionic bond. And if we want to get colorful on you, look out. If we look right here, the bond between the carbon and nitrogen, 1, 2, 3 pair of electrons, is a triple bond. So in potassium cyanide, there's an ionic bond, one of them, and a triple, covalent triple bond. And that's how you do it. Now, I talked about, and I'll just talk about briefly, shapes of molecules. Molecules are not all flat. They have different shapes. And the Lewis structures show the number of bonds and types, but not the shape. And molecules exist in 3 dimensions that have shape. And the shape is determined by the valence electrons and the type of bonds. Now, switches off. This is called the Vesper Theory, which stands for valence shell electron pair repulsion. Electrons having the same number, having the same charge, negative, when they're in a pair, want to stay away from other pairs of electrons because of repulsion. And therefore, if you've ever played with a magnet and put the 2 north poles together, they push apart. Well, same thing in molecules. And by having the greatest distance between pairs of electrons, determine the shape of molecules. And they're different ones depending on how many Vesper, and this should be a capital R, electron pairs you have. And it can be linear, trigonal, tetrahedral, if you have 4, or trigonal planar or angular. Let's talk about what that means. Let's go out on the internet. And let's get to this chart I want to get to. And now you can see it. This is from Wikipedia. And I've mentioned Wikipedia is so heavily policed by chemists like me that it's been a number of years since I've seen something chemical. Other stuff I don't know about, but chemical, and it's valid. And here are the different shapes depending on how many different valence pairs of valence electrons there are, and also how many lone pairs. And if we look at 3 of 4 bonds to a center atom is tetrahedral. And if you look at methane, CH4, which is your natural gas, is tetrahedral. Now, ammonia, NH3, has 1 pair of non-bonding electrons and 3 pairs of single bonds. And it has a trigonal. Now, water, and you see the pretty picture, has 2 on the oxygen, 2 pair of non-bonding electrons and 2 pair of single bonds. And water has the shape of bent. Trigonal looks like this. Tetrahedral looks like that. Oh, those pretty pictures. And use those in organic more than inorganic. And there's bent. And that causes the shape. And they show here Water's bent like this. Let's go to ammonia is trigonal like that, planar. And let's find natural gas. It's got a tetrahedral. And these shapes play an important role in our life, like how your skin's bonded together, even your RNA and DNA, the shape of that. The bonding electrons play and non-bonding play an important role. But you never thought the shape of your RNA and DNA was due to electrons, valence electrons. They are. All right, another thing I'd like to talk about and switches off, that's called electronegativity. And electronegativity is the measure of the relative attractance that an atom has for shared electrons. And it's the same, how strong am I? And the stronger I am when we're sharing electrons, I can share them closer to me. And as you look at the periodic table, again, switches off, but I'll talk about something important in a little while that is based on electronegativity. But let's take a look. When you move from left to right in a row of the periodic table, atoms are more electronegative. When you go from bottom to top of a column, atoms become more electronegative. The most electronegative atom in the periodic table is fluorine, and oxygen is more electronegative than water. And this causes a slight shift in the electrons, which we call a polar. And now I'm going to turn the switch off for nonpolar covalent. That's when you have equal sharing. When it's not equal sharing, you have polar. And this I'm going to talk about and think about two people sharing an umbrella. Well, what does this mean? Well, let's look at water. And if I draw it this way, and Dr. White, being an organic chemist, used the line instead of dots, and here's the Lewis structure for water. Let's do a second one. And because oxygen is more electronegative than hydrogen, there's a slight charge, which we show by lowercase delta. And delta is from the Greek alphabet. In chemistry, this is delta uppercase, and that means difference. And when we do this, this is lowercase delta. And that means little difference. So because of the electronegativity difference between hydrogen and oxygen, there's a slight negative charge on the oxygen. Each of the hydrogens have a very tiny positive charge. Now, think about two people in a rainstorm. Don't tell my sister I'm telling this story. When I was very little and she was 7 years older and she was much bigger than me, guess what? We were out walking home and we only had one umbrella and it started raining pretty heavy. So we shared it. But she was bigger than me and stronger at that time. Not anymore, but back then, because I was just so little and she was much older, 7 years older, and she held it more over her. I sort of didn't get too wet, but I got wet because she was bigger. And as we say in atoms, she was more electronegative at that time. Well, it turns out this happens. And if you look at this oxygen, it has a negative, slight negative charge. And this hydrogen has a slight positive charge. And there's a very weak attraction between those. And this, I'm turning the switch on full blast. If it was a dial at 1 to 10, I'm turning it to 50. And what this a slight attraction we call hydrogen bond, or sometimes hydrogen bonding. And it's not a true chemical bond, but it's a very weak attraction. And that little force has played a major role in our life. Because of that, hydrogen bond in water, H2O, water exists at room temperature as a liquid. Ooh, nice liquid. But you can see it's a liquid. Other molecules with the same molecular weight, which I'll teach you what that means later on, should have the same physical property. Is it a liquid or solid or gas at room temperature? And it doesn't. Those other molecules are gas. Why the difference? Hydrogen bond. And just think, on our planet, if water had been a gas at this temperature, room temperature, instead of a liquid, well, we wouldn't be the same, because your blood wouldn't be a liquid, it would be a gas, because your blood is mostly water. It wouldn't even be blood, because the other things that are in your blood couldn't be in there because it was in a gas, and they'd still be a solid. So hydrogen bonding, important? Yes. And hydrogen bonding, let's see if I have a slide for this. I don't. Hydrogen bonding occurs molecules or atoms, oxygen, nitrogen, and fluorine, with a hydrogen on it, meaning the atom oxygen. So water will hydrogen bond, ammonia will hydrogen bond, alcohols which have oxygen and hydrogen in them, such as rubbing alcohol, and the compound hydrogen fluoride, which is a very dangerous compound. I'll tell you a story about that another time. And so water, ammonia, alcohol, and HF can all hydrogen bond. And these are sometimes called polar molecules, or anyways. And if we look at this, oh no, we've gone to the end of the chapter. And as I look at the clock, oh no, we're at the end of our time for this lecture. And I hope you enjoyed my do-it-yourself lecture, because something happened to the original video. But what that means is Dr. White can say goodbye, gang gesund. I'll see you soon, and have a nice rest of the day, and I'll see you in the next lecture. Bye, gang gesund.